All right, the golfer. All right. Greg Michelson. All right. All right, let's go ahead and get started. Let me go ahead and get the sign-in sheet passed around. So a couple things. You all have your homework 8 posted on Blackboard. It is the last assignment of the semester. I have a few hard copies up here, which means you might not have them. Excuse me. In addition, I also have homework, I have your lecture notes for columns up here. What I'm going to do is I'm going to finish these. I'm going to try and finish these lecture notes today. We'll see if I can get through them. If not, they may bleed a little bit into Monday, and then we'll finish your last slides on beam columns. Now, next week, I'm going to bring in the notebook with all the lecture note handouts and homeworks and homework solutions. So next week, make sure that you've got everything ready and you can give it the once-over and make sure that you've gotten everything. One other piece of info for everybody. I did this last semester, so those of you that had me last semester know about this. But one of the things about Marshall is that since they don't make you do your course evals, the turnout across the university can be pretty low. So what I do is if you show me proof that you've done them, you can, what was the expression, rake me over the coals if you want. That's totally fine, but I just want you to do them. If you do them and show me that you have done them, I'll give you 5 bonus points on your homework average. So, excuse me. So I think, if I'm correct, you all can go on to MyMU and it'll show you which ones you've done and which ones you haven't. If you just screen capture that, automatic. So, yeah. So, I mean, it helps, yeah. An Amazon review? I'm not a book. I don't know how I'm supposed to respond to that, sir. Is that a compliment or? What's that? It's better than the pinky thing. Yeah, I guess it is. In case, or I don't know if I've told you all this, but my very first semester that I was here, I broke my pinky. And I tell people it's because I was fighting a group of international assassins, because it's so much better than the truth, which was that I was taking out the kitty litter, and my finger got caught in the door. And on my first ever set of course evals as a college professor, somebody wrote, other than Dr. Michelson walking out with his finger stuck out like a little wimp, the class was great. And I love that comment. I still want to know who did that just so I can shake their hand. I still don't know who did that to this day, but yeah, she said she knew who said it, but she wouldn't tell me. Yeah, say, tell me when you graduate. Just let me know. I'll go back and change your grades. No. That's true. I'd have to shake their left hand. Yeah.
I really thought you wrote that you fought hundreds of international students for some reason.
No. But like, I'm having to sit there and write on the board, and I'm like writing on the board like this. Well, I mean, how many of you had me for geomatics that semester? I mean, it was like this. It was ridiculous. I had a bandage like that. It was pretty bad. Oh, there was a splint in there and whole 9 yards, yeah. It might have just been by instinct, like over there. The only thing I remember is I kept closing people's, total station cases. Everybody kept leaving them open.
We kept sucking at it. David never mentioned a thing until like the last lab.
Oh, by the way,
Yeah, because I was like, hey, get the tree behind that one. He's like, which one's that? I'm like, the one that's farthest away. He goes, I don't have depth perception. I'm like,
all right, back to the world of concrete design. Um, so we were last time we did an analysis problem of a square column. Today we're going to do an analysis problem of a circular column, and it'll be a fairly short one, and hopefully we'll be able to get into design today. What I want to do though is get a little bit into the world of spiral columns. So, excuse me. So tied columns, the way that they fail, if you recall, once the concrete spalls outside the rebar and the rebars begin to buckle, it's over. The column's gone. Spiral reinforced columns, on the other hand, they serve to contain the concrete inside the core a little better. And it's a lot like a pressure vessel that you all did in mechanics of materials. You have a cylindrical pressure vessel. There's a pressure inside, and you develop that radial stress and that hoop stress. I know you've done it before. I know I did it with my deformable folks.
You say that like we actually did.
Oh, yes, you did. Oh. Oh. Oh, yes, you have. Yes, you have. All right, all right, all right. So the idea behind the theory is that once the concrete on the outside of the cage spalls off and fails, you've got this core of concrete inside your spiral reinforcement that's being subjected to compressive load, and it's a lot like a pressure cylinder. You have a cylinder, you take a compressive load, that cylinder develops internal stresses. The same provisions that come from that are what we use here. So for the shell strength, we say, all right, it's the 0.85 FC prime gross area minus the area of the core, that core inside. Now for the spiral, we basically say, all right, it's the 2 times the reinforcement ratio times that area. And that 2, that basically just comes from the pressure vessel analogy that you did in mechanics of deformable bodies. I know you did it. I promise you did. I promise. Okay. So basically the idea is that you're setting these two equal to one another, and the idea is you're trying to determine, do you have enough of a spiral reinforcement ratio, enough of that spiral steel to resist the capacity of that load inside the core. So you're basically just setting the two equal to one another and solving for rho. Now, what does the code do? Technically, the math comes out to be you get a constant of 0.425 because you take that 0.85 and divide it by 2. Code says, what the heck? Just round it, keep it simple. So that's where you get that reinforcement ratio. Now, how do you actually compute that reinforcement ratio? It's a little different because it's not just area of steel divided by area of the concrete, because you have to consider you're trying to determine that percentage of steel spiraling up the column. So the way that we compute that is we say, all right, it's the volume of the spiral divided by the volume of the core to kind of get that percentage. Now, how do we do the volume of a core? Well, we're looking at that percentage within a given pitch, within a given increment of spiral spacing. So for the concrete, it's the volume of a cylinder. And how do you calculate the volume of a cylinder? Well, it's the area times the length. So the area is pi d squared over 4, the diameter of that core, and the height is just that pitch, that S. Now, how do we compute the volume of the spiral? Well, the volume of the spiral, basically what we're doing is we're taking the area times the length. And that length is essentially the perimeter around the circle. So that's where we get the area of a single, of one of those spiral bars, and then the perimeter. And how do you calculate the perimeter? It's pi times the diameter. Why are we subtracting a bar diameter? Because you have to come in half a bar diameter on one side, half a bar diameter on the other. So this is what you see in this box. This is the actual reinforcement ratio that you're getting from that spiral reinforcement, and that's your limit. Okay, so as long as you have more than that, good to go. All right, does that make sense? Good stuff. All right. So we're going to look at the design axial load of this column. Think you're going to find that it's a pretty straightforward analysis. The only thing that changes are some of your constants in your some of your constants inside your capacity equation. The phi is different, the alpha is different, but ultimately the capacity is pretty straightforward. In addition, we're going to do that spiral check, and I think you're going to see it's pretty plug and chug. Okay. Yes, sir. Bar diameter. I can see how that would be confusing. It does. It's very common to use that symbol to represent a diameter. So, yep. That's pretty common. Okay. So, let's look at some column parameters. All right. So we've got our typical material parameters. All right. Now, for our longitudinal steel, we have 7 number 8 bars, okay? Does anybody remember how to calculate the area of that? There you go. And what is the area of 7 number 8s? What's that? No. That'd be if it's number 9. What's that? No. Hold on. You remember this? Remember that? So 7 bars that are number 8 in size, the area is 5.5. Remember that? All right. Now, we have a diameter of the column of 15 inches. And what is the area of a spiral bar? What are the spiral bars? They're number 3s, right? So the area of a number 3 is 0.11, right? Y'all okay with that? All right. Excuse me. So for the design capacity, it's pretty straightforward. Okay. So we're dealing with a spirally reinforced column. So what's phi? What's alpha? Okay. Make sense? Now, how do we calculate the gross area of the column? Before, it was just rectangular, so it was b times h, or b squared, because it was really a square column. How do we calculate the area? It's a circle, so there we go. Pi over 4 d squared. Not too bad, right? All right. So, So to calculate phi PN, we say phi times alpha, and then we've got 0.85 FC prime times the area of our concrete, which is just AG minus AST. Oh, a little high. Plus FY times AST. So filling this in. So somebody help me out. What we got? Making y'all do some work on a Friday? Goodness. I'm horrible, aren't I? Is that what everybody else is getting? There we go. That's it. Well, we also going to check the spiral steel, but in terms of capacity, yeah, that's pretty much it. Nope. True, but even then, that's a pretty plug and chug expression. You like this stuff? Honestly, the beam column design and column design, it's pretty simple. It really is. That was a good one. He said he hopes it doesn't spiral out of control. Just saying, when you graduate and you're gone, I'm taking credit for that one. Just saying. All right, has everybody got everything within, does everybody have everything on this? Am I good to move on? Okay. Not Dr. Michelson YouTube page. That really sounds like the name of a comic book villain or something. Grag. I do this the whole time. All right, spiral steel check. Okay, so it's pretty straightforward. I'll walk you through a couple things. So we first off need to calculate the diameter and the area of the core. Okay, now the core, what we do for that is we say, all right, and we keep it simple. We say, well, the whole column is 15 inches, right? And the cover is 1.5 inches, right? So we just come in 1.5 inches on each side and say the core column diameter is 12 inches. So we can calculate the area of the core by saying pi over 4 DC, or DC squared and get that. Okay, so it's pretty straightforward. We start off by computing our spiral reinforcement, what we actually have in terms of a ratio. So we're calculating the volume of steel in a single pitch divided by the volume of concrete in a single pitch to get that reinforcement ratio. And that is 4 times the area of a spiral, DC minus DB, in that core diameter, but we come back off of we come back 1. And then S DC squared. So 4 times 0.11 inches squared minus. Now, remind me, what is the diameter of a number 3 spiral? 3/8. There we go. Remember, number 3 to number 8, you divide it by 8. What's the the pitch? What's the pitch of our spirals in this problem? 2 inches. Plug and chug, and what do we get? About like that? All right. So about 1.78% spiral reinforcement. Let's see if that's enough. So rho S minimum is that 0.45 AG AC minus 1 times FC prime over Fy. So that's that pressure vessel analogy, just rounded up a little bit for conservatism. So 0.45 times, what's the gross area of the column? We did that before. And then 113.1. What do we have here? So maybe something like this. Like that. All right, are we good? There you go. That's it. Did that spiral out of control? Stock drag. Thank you. In all honesty, I mean, like axially loaded columns in concrete, it's pretty simple. Yes. Well, okay, that's a good question. And what I'll say to that is this. Spirally reinforced columns, you confine your core better, you get a bump from your eccentricity and your phi value, and down the road, if you ever run into things like seismic demand and what have you, they perform better in seismic situations. So good question. Where'd my little mouse? Okay. What? Well, we're going to talk about design here in a little bit. The design is, again, the design is simple, okay? let me explain how design works. So if you liked the analysis, you'll probably like the design as well. Okay, all right. So column design is pretty straightforward. You start off by saying, all right, let's figure out our factored load, 1.2 dead plus 1.6 live. Let's take a wild guess as to what our reinforcement ratio needs to be. It's got to be between 0.01 and 0.08. That's code limits. A good starting value is 0.02. 0.03 is not the worst idea in the world. Most of the time, I'll dictate that to you, what you need to use for a starting value. But if you don't know, 0.02 is a good place. Now, here's the thing. You're going to do that so you can solve for the gross area of the column. Now, what's going to happen is you're going to say, all right, let's solve for the dimensions of the column, and you get 15.82 inches. Are you going to design a column that's 15.82 inches wide? No. You're going to say, let's use 16. So you're going to take the column, and you're going to use a different size. So now that you've got a different column size, go back and solve for the steel that's required. Okay? After that, check your details. That's it. So here's how this works. So in order to determine the required gross area right here, basically what you do is you set VPN greater than or equal to PU, and you solve for the required gross area, and it's pretty straightforward. We make a blanket assumption right at the beginning that the area of steel that goes into that column is the gross area of the column times this assumed rho g value. That's where that 0.02 comes into play. So assume a rho g value, plug and chug. You'll get a gross area of the column. Then you've figured out your dimensions. Take those dimensions, plug them back into the expression, solve for the area of steel. You can't just take that new column and take it and multiply by 0.02 to get a steel. You have to actually go through and compute it because your column dimensions at that point are different than what you solved for. So, but in the end, I mean, everything's already derived for you. It's pretty plug and chug. Solve for your gross area, pick a column size, solve for the steel. Pretty straightforward. So we're going to do two column design problems. We're going to design a square column to support a dead load of 130 kips and a live load of 180 kips. We're going to begin using 2% steel, so at 0.02. There's our concrete strengths and what have you. And then we're going to do a spiral column. Same deal. All right, sound good? Pretty straightforward. Okay. So let's start off with A. Dead load of 130 kips, live load of 180, 2% steel, 4 KSI, 60 KSI, concrete and steel respectively. All right. So now we are in column design mode. So we've got our, I'm going to put it like this, our starting row value is going to be about 0.02. That's going to be our starting value. All right? We've got a, we've got a dead load of 130 and a live load of 180. What's first step? Factored loads. Should be old hat by now. I have a feeling some of you have already done this. What do you get? There we go. All right. So now if we go into column design, if we're dealing with a tied column that is square, what's phi And what's alpha? Therefore, our minimum gross area, and again, this just comes from taking phi-pn, set it equal to pu, make a guess on your steel, and solve. It's pretty straightforward. So on the bottom we have phi alpha whoop, I'm getting ahead of myself. All right. So it's pretty plug and chug. So watch this. We got on the bottom, we'll draw that out a little bit, 0.65, 0.8, 0.85, 4 KSI, 1 minus 0.02, plus 60 KSI, 0.02. The design load is 444 kips. Well, what do you get? $192? I got 188.4. What? I got 188.4. Did I plug something in wrong? Oh, well, I forgot a bracket. Anybody else check me on that? $188.4. Anybody else get that, or? Okay. Maybe a parenthesis somewhere. So if this is a square column, how do I determine what the sides of those columns are? How do you calculate the area of a square? There you go. So B min is the square root of AG min hold on, let me do something. Move that down a little bit. What do you get? What do you think we ought to do? Not too bad, right? Straightforward? All right. So I'm probably not going to have room, so can I go ahead and go on to the next panel? All right. So AST, and again, this just comes from your plug and chug, your second plug and chug expression. You get, I'm drawing that really long just because I want to have room. All right. So again, just plug and chug. So on the top, 444 kips minus 0.65, 0.8, 0.85, 4 KSI, 196, and then 0.65, 0.8, 60 KSI minus 0.8, oh, nope, sorry, 0.85. And what are we getting? $3.312. Everybody else get that? Not too shabby, right? Okay. Now, that is the required area of steel. How do we actually go through and select, what we need? Well, that's where this comes into play. Remember that? That should look familiar. All right. The longitudinal steel. Longitudinal steel. And there's no spirals. This is a square column. So it's just ties. All right. So help me out. Let's see if we can make sense of this. Let's pick a couple options. Let's see. Bar number, maybe number 6. Maybe that one. 3.53. That'd be a good one. There we go. 10/18s. That's like the W14 by 800 in steel designs. Like whenever in doubt, just pick the W14 by 800. It'll work every time. Yeah, you won't be in business very long. Now, that one works, right? 5 number 8s. 3 number 10s. Now, and then right there. What's that? Well, we're going to get to something, and you bring up an interesting point. It's a square column. What is the least number of bars you can have in a square column? 4. So you can't use this. Even if it's the most economical selection, you can't use it. Okay? So we're left with options of 4 bars, 5 bars, 6 bars, or number 8. I like things symmetrical. Would the 5 bars? You could, but then you'd have to tie it together, and you need extra steel just to put that 1 bar in. That probably ain't going to work. So which one do you think would go with? 8 number 4s. So that's the one we're going to go with. Does that make sense? So I wanted you to understand that logic behind why we selected the bar pattern that we did. An even number of bars makes sense. We can't go below 4 bars, so we just pick the one that has the least area, and that's it. So 3 on each side, yes. What? Well, yeah. There's nothing wrong with that. Well, it just depends about how your column's oriented. But what we're talking about lends more into our beam column discussion later. So, let's see. our tie selection. Okay. Now, with ties, well, hold on, let me write this down. I'll say use 8 number 6s. Is that what we said, 8 number 6s? Okay. All right. Tie selection. We go with either a number 3 or a number 4. Which one do you think we ought to go with? Yes, sir. We picked this one right here. We picked that one. Yeah, the 350, 3.538, number 6. Yeah. It's starting to spiral out of control. It's starting to. Not quite there yet, but I just did. This isn't hydraulics. All right. So our tie selection. We're really going to go with either number 3s or number 4s. Which one should we go with? Why? Well, but there's a reason why. What's the difference? Remember, you use number 3s up until your longitudinal bars are a size number 10s. Remember that? And then anything up above number 10, use the number 4. Our bar size that we selected was a number 6. So we'll say, since longitudinal bars are smaller than number 10s, use number 3 ties. Now, in the world of design, I would prefer to use the least amount of steel possible. So in terms of spacing my ties out, I'd want to go with the maximum tie spacing possible, right? So let's look at maximum tie spacing. And if you remember, we have 48 tie diameters, which is 48 times 3/8, which is what, 18? We've got 16 longitudinal bar diameters, which is 16 times, what's the diameter of a number 6? 6/8 or 3/4 or 12 inches, and the least column dimension, which is what? Make sure y'all pay attention. What's 14? So we have to go with the minimum one of those. So I'm going to say use number 3 at 12 inches. Oh. So what does my column look like in the very end? Looks like this. Eight number 6s, we have go ahead and go with a 1.5 inch cover just to be, consistent. 14 by 14 inch column. And that's it. There's only two other things we have to check, which they're really short. So, but does everybody understand what we just did? And there you go, that's it. That's a good question. So let me go off on the side a little bit. There was a question raised about the homework in relation to development length. There were some additional psi values in the book than there were in the lecture notes. The reason why is twofold. Number one, the actual output of the specification did not change at all. If you go back to the lecture notes, there were two reductions based on cover and stirrup spacing, and it said, if your cover meets this requirement, multiply it by 0.7, and if your spacing meets this, multiply it by 0.8 or what have you. That's what the psi r and psi t were. But if you look, everything should come out to be 1, and then it doesn't matter anyways. So it was all the same. Let me go back to this. There's a couple things I need to check real quick on this. So I'm going to sort of, I'm going to check two things. All right. We had a row ratio that we started out of 0.02. That was a guess. We need to check what we actually got in the end. So row G, I'll say actual, is 8 number 6s, which is, let's say area of steel divided by the gross area, which is 3.53, 196. So that's 0.018. Is that good? It has to be between 0.01 and 0.08. But remember, we selected 0.02 for the purposes of design. We didn't get that in the end because we iterated where our column dimensions changed and what have you. So there's that. And then our clear bar spacing. Remember, that's got to be less than or equal to 6 inches. So let's see if we remember how to compute that. We take 14 inches, we subtract 2 covers, we subtract 2 ties, subtract 3 bars, 3 longitudinal bars, and divide that by 2. Y'all remember that? You do that, and you get exactly 4 inches. Is that good? It's got to be less than 6. If that came out larger, you've got a couple options. Either A, pick a new steel layout, or B, maybe increase your cover a little bit. Make it 2 inches of cover, and then it's funny how your bars shrink up a little bit. Comes in. Sound good? That's all I got for you all on this. I think I'm going to give you a handout on circular columns, or we might go through it. It just depends on our timing. And then Wednesday, for sure, it's beam columns. But it's actually really simple in terms of design. That's all I got. I will see you all next week. Y'all have a good weekend.